You probably don't think about how your email app remembers that you archived a message 6 months ago. Or how Netflix knows which episode you paused halfway through. These aren't accidents. They're deliberate and intentional choices. Quiet, invisible rules by engineers about how information should be stored. And at the heart of these choices is a question that's older than the iPhone, older than Google, older than the web itself. How do you organize information so that millions of people can access it at the same time without losing a single piece? And there's an answer that has shaped databases for over 50 years. And a different answer that emerged more recently in order to handle billions of users. Two, but very different philosophies that shape the way systems function today. And the difference between them shapes almost every piece of software you touch. One philosophy says, organize data into tables with strict relationships. The other says, organize data into flexible documents that can change shape. These are called relational databases and NoSQL databases. A relational database organizes data in tables with strict connection rules. Imagine a shopping cart system, designed to track items and customers. One table holds products. Each row has a price and ID. Another table holds customers. Each row with an email and shipping address. A third table holds cart items. Each row connects one product ID to one customer ID, with a quantity. These connections are enforced through foreign keys, ensuring referential integrity across tables. When you ask, which customers have purchased this sweater? The database looks at the products table. It finds the sweater. It follows the connections to the cart items table. Then to the customer's table. This is called a join. It's powerful because the database understands the relationships. It enforces rules. This works best when data is predictable. If you delete a product, it can automatically remove all cart items linked to it. If you try to add a cart item for a customer who doesn't exist, it stops you. This structure works beautifully when your data is predictable, interconnected, and needs consistency. But it has limits. Every piece of data has to fit into a predefined table with predefined columns. If you suddenly need to store something new, like a gift message or custom engraving text, you have to modify the table structure. And if millions of people are accessing the database at once, spreading it across multiple servers becomes complicated, because those strict relationships have to stay intact everywhere. A NoSQL database takes a different approach. Instead of tables with rows and columns, it often stores information as documents, each one a self-contained bundle of related data. In systems like MongoDB, these are JSON-like documents with flexible schemas. One document might hold an entire cart. The customer's email, their address, a list of products they've added with prices and quantities. There's no separate table for products or customers or cart items. Everything related to that cart lives in one place. This makes some things faster, because if you want to load a customer's cart with all its details, you get everything in one read. No joins. No hopping between tables. And it's flexible. If one customer needs to store a gift message and another doesn't, that's fine. You just add the field to the document that needs it. But this flexibility has trade-offs, because the database doesn't enforce relationships the way a relational database does. If you store the sweater's price in every cart document and the price changes, you have to decide whether to update all existing carts or leave them with the old price. The database won't enforce consistency for you. And if you need to answer a query that spans many documents, like show me all carts containing this sweater, the database has to search through many documents instead of following a clean connection. Here's something that matters more than most people realize: what happens when something goes wrong or when you need to understand what's happening in your system. With a relational database, you can ask questions using SQL, a language designed specifically for interrogating structured data. You can write, "Show me all customers who added a product to their cart more than 7 days ago but never checked out, grouped by product category." The database answers in seconds because it understands the relationships. You can explore your data interactively. This ad hoc querying capability becomes critical for debugging, analytics, and business intelligence. With a NoSQL database, that same question becomes harder. Because the data isn't organized around relationships, you often can't ask these kinds of questions as naturally. You may need to write custom code to scan through documents or design the queries in advance. But NoSQL databases excel at different things. When you need to add a completely new field to your data, you just add it. No migration scripts. No downtime to alter table structures. Or when you need to split your database across dozens or hundreds of servers to handle massive scale. NoSQL databases are built for this. This is called horizontal scaling, and it's much simpler in NoSQL systems because documents are self-contained. Each server can hold a portion of the documents without needing to coordinate complex relationships across machines. And when you need to retrieve a single piece of data with all its related information, you get it in one operation instead of assembling it from multiple tables. So which architecture is better? Relational databases or NoSQL databases? The answer is neither. Because it depends. When engineers choose how to store data, they're not just choosing speed or flexibility. They're also choosing how maintainable their system will be years later. A relational database says, "I promise this information is consistent and correct, even if it takes a moment longer, and you can ask me anything about it later." A NoSQL database says, "I promise this system will stay fast and available, even if some information takes a moment to sync, but you need to know your questions upfront." These promises affect trust. If your bank used a NoSQL database that prioritized speed over consistency, you might see your balance update before the transfer is fully completed. That would feel broken. If a messaging app used a relational database that enforced perfect consistency across millions of users, it might become too slow to feel real-time. That would also feel broken. The invisible architecture behind software determines whether it feels reliable or fast, rigid or adaptable, trustworthy or fragile, and whether engineers can understand and fix it when things go wrong. These decisions compound. A system built on strict relationships can handle complexity and unexpected questions gracefully, but struggles to scale infinitely. A system built on flexible documents can scale beautifully, but requires careful design to avoid inconsistencies and can become harder to debug and analyze. There's no perfect database. There's only the right one for the problem. Large systems often use both. Consider a banking app. The part that handles your bank account might use relational tables with strict consistency. The part that shows you a feed of updates might use flexible documents that scale across hundreds of servers. You only feel the consequences when something breaks. That's when a developer somewhere is trying to understand what went wrong, hoping they organized their data in a way that lets them find the answer quickly.